today I was debating, since there's just one lecture, I want to give you some unit which is both interesting and has open problems to think about. And then I remembered a saying I heard from Aldous, which said that the good warm-up for working on large finite graphs is to work on infinite graphs. So, and actually that's how I myself and several other people like Laurent Salov-Kost, who've been, have worked on Markov chains on finite graphs, we somehow came from the infinite graph world. So, by the way, can you hear me? I don't know, can people in the back, can you hear? Yes, okay. So is there a way to make this
clear? Because if they don't hear, they cannot answer that they can hear.
That's right.
People in the back, can you hear Yuval? Not me, I'm sure about it. Yuval, can you hear? You should say something.
Okay. That's remind me, right? It's the hardest job is a door-to-door salesman of hearing aids. So, okay. So infinite graphs. So, for instance, if you want to understand, if you take the graph G and P, say with P, which is 2 over n, and you want to understand the random walk on this graph, how fast does it move away from its starting point? Well, again, because the graph is finite, eventually it gets stuck. But how fast does it move initially? To understand that, you want to understand the local structure of this graph. And locally, this graph looks like approximately, so it's locally converging to a Galton Watson tree, a branching process, with the offspring distribution, which is just Poisson 2. Right, so you have Poisson 2 number of children in this tree. And then the graph locally around the vertex looks like a Poisson 2 tree. And then to understand the random walk on this graph in its initial stages, you want to understand random walk on this tree. So let me indeed start with this example. So in fact, you were supposed to have a whole course on this random walk on these kind of random trees. So you won't get a course on it, but just I'll give you a glimpse. And we have, so Gerard Ben-Arous didn't make it here, but Vlada Sidorovicius was here, and Alex Friberg is still here, so I'll mention something from their work as well. So consider a random walk on this kind of random tree, but the Poisson 2 tree is an example of a tree that can have leaves, right? So a vertex could have no children. So I'm going to simplify matters right now and consider for a moment a random walk on Galton Watson trees with no leaves. So here is an example. So suppose the number of children is either 1 or 2 equally likely. So every node has either 1 child or 2 children with equal probability. Okay, so you just keep growing this tree. So we understand the growth of this tree very well. The mean number of offspring of every vertex is 3/2. So consider this infinite tree and consider simple random walk on this tree first. Okay, so the first question I want to ask, and maybe we can decide this in a democratic fashion, how fast does the random walk escape on this tree? So here is one argument. If we look at the vertex, right, half the vertices have degree 2 because they have 1 child, and half the vertices have degree 3 because they have 2 children. So let me call this argument 1. It says that the speed should be, so by the speed I mean I look at how far the walk has moved in t steps, I divide by t, and I want to take the limit as t tends to infinity. If you want, take the expected distance traveled, divide by t, and take the limit. The limit will exist. But now let's just intuitively see what we would guess. So one argument says that the speed, well, with probability half, if we're at a vertex like this, then there is no drift. We are equally likely to go back and forth. So in this case, we'll get the contribution of 0. And with probability half, we'll be at a node like this, where with probability 2/3 we'll move forward, 1/3 will move backward. So we'll get 1/3. So this argument gives 1/6. But then maybe this argument is naive. So argument 2 says, well, remember that a random walk on a graph doesn't visit all vertices with the same frequency. We know that it visits vertices, at least from our experience with finite graphs, it visits vertices with frequency proportional to the degree. So these vertices should be only visited 2/5 of the time, and these vertices should be visited 3/5 of the time. So maybe the speed is 2/5 times 0 plus 3/5 times 1/3, which gives 1/5. Okay, or maybe it's something else. So I'll make life easy by saying the speed does exist. So if you take the distance at time t, divide by t, this does converge almost surely to a constant. And we just want to determine what it is. So I gave you two arguments, and we could argue all day, but let's just decide democratically what happens. So please no abstention. So let's just vote. So we have three options, either this one, or maybe another value. So, all right, who votes? Or do you have any questions to clarify? Because you should be.
Why it works on Z, this argument?
Sorry, on Z the speed is 0, and it works just fine. Every point has.
Yeah, sure, but like the average distance, well.
No, this is an argument at the level of first order, at the level of this, and it works very well on Z. So, it works well if you have, say, a regular tree. So, right, if you have a regular, say, B-ary tree, so every vertex has B children, then this argument says, well, with probability B, right, so the argument says that with the probability we move forward, we have B children, so the probability we move forward is B over B plus 1. The probability we move backward is 1 over B plus 1. So the speed should be B minus 1 over B plus 1 on a B-ary tree where every vertex has B children, and that's correct. So formally, if you take the location at time t and subtract the sum of these local drifts, you'll get a martingale. So you know that this difference will be small. So this speed does behave like the sum of the drifts. So the issue really is to understand the frequency of visits to different vertices. Okay, so any other questions? Because I'm sure you want to be informed voters. You don't want to vote without understanding the issues. Okay, so please raise your hands high. Who votes for 1/6? Okay. Who votes for 1/5? Boy, this is tough. Who votes for some other value? Wow. I don't know. We'd have to do a recount.
You know that here in local elections up till recently there was always possibility to vote against everyone.
I see.
But A, B, or C, or against everyone.
Well, but here C was everything, all other possibilities. So I think already I gave this option in the third thing. So we would have to do a careful count to decide the winner here. But anyway, the truth is 1/6, and but I should say that there was a. So this is actually from very old joint work in '95 with Lyons and Pimentel. But there's a reason I'm telling you this, because there is still an open problem related to this. But just so you don't feel bad, there was before, I mean, people say who voted for 1/5 should know that before our paper, there was a paper by David Aldos considering another problem where he mentioned in passing that, you know, clearly the speed should be 1/5 in such examples. So, yes?
Can you give an obvious example where the argument 1 doesn't work? Something simple like this.
So, well, take okay. So I'll give you soon. So just hold on, and in 2 minutes you see it. I just want to explain this calculation first. So the reason this works here is because the frequencies really are given in this case by these numbers, but how do we know that? Because we can find in this case an equivalent invariant measure that we can describe explicitly. So what is this measure? So if this is a Galton Watson tree with this distribution, let's create another Galton Watson tree with the same distribution, independent, and join them by an edge, and put the root at one of the nodes like this. So this is a new distribution on random trees where the root, instead of having z children, it really has, so the total number of children of the root, if z is the offspring distribution over there, the total number of children here is z plus 1. Okay? And you can think of this, if you take the binary tree, right, every vertex has degree 3 instead of the root. So to make it really regular, what you do is you can take 2 copies of the binary tree and join them by an edge, and now you have a 3 regular tree where everything is more symmetric. So you can do the same thing in this case, in the Galton Watson case, and what you find is that this measure, this random tree, gives you a invariant distribution for the environment seen from the moving particle. So if the particle starts here, and now it takes one step of a simple random walk, and it looks at the distribution after that one step, it will see exactly the same distribution as it had initially. So it's clear if it jumps here, this is the same thing, but also if it jumps here, what it will see will also be, you know, this vertex will have degree z plus 1, and all the other, and then after that it will continue with Galton Watson trees. So you can easily check that the statement, and you know, there is a paper. It appeared in the journal Ergodic Theory Dynamical Systems 17 years ago that discusses this in detail and says this is an invariant. So we have formally a transformation here where we move from, if you want, we have a Markov process on the space of trees where when we move the particle, we actually then reroute the tree at the new location of the particle, and we see, look at this new tree with the new root. So this is defines the Markov process on the space of trees, and this measure I'm showing you is an invariant ergodic measure for this Markov process. It's, again, not hard to verify. Once you know that, then this argument with the drift can now be easily made rigorous, because from the ergodic theorem we know that the frequency of visits to different vertices is just given by the probability under this invariant measure once you verify the invariance. And indeed, under this measure, vertices have, in this case, degree 3 with probability half and degree 2 with probability half. But this is just because, you know, the naive argument which gave 1/6 happens to work here, but it still had a gap. So luckily, you know, it turned out to be right. So now let me answer Vladislav's question. Let's look at a slightly different process where we bias the walk. So this is, let's see, where is this eraser? Okay, so let's look at a different process where we bias the walk. So this is what, so this is the lambda biased walk. So we have a parameter lambda, and to be interesting, lambda should be between, well, I shouldn't say that. So lambda should be positive, and we'll take it to be less than the mean number of offspring, which in our case is 3/2. And at every node, we put weight lambda on the edge pointing up towards the root, and weight 1 on the children. Okay, so we do this at any node. We look if it has 1 or 2, we put lambda on the parent and lambda on the edge leading towards the parent, and weight 1 on the edge leading away, and we take a random walk which walks proportional to these weights. If you want an explicit description in terms of conductances, you can think of putting a conductance of lambda to the minus k on edges at level k, and then just walking according to these. Right, so you could, if you want a consistent set of conductances, you could put 1 and 1 over lambda here, and then 1 over lambda squared here, and so on. And these will be the conductances, and then you take a walk proportional to these conductances. So look at this walk. It's lambda biased, and for lambda which is between 0, so again, I'm considering trees that have no leaves. So every vertex has at least one child. So for all these values of lambda, the walk is transient and it has a positive speed. But what is the speed? So again, the naive argument we used for here would suggest that maybe the speed would be with probability 1/2. So the speed should be, we move forward with weight, so 1 minus lambda over 1 plus lambda. And with probability 1/2, it should be, so we move, right, so if we are at a vertex, like this, lambda 1, 1, then we move forward with probability 2 over 2 plus lambda, and we move backward with probability lambda over 2 plus lambda. So the same naive argument that led us to 1/6 would lead us to this for the lambda biased walk. But this is wrong. So maybe this answers your question, I'm not sure. So because when the naive argument I gave for 1/6, I didn't justify why is the frequency just given by the original probabilities. And it happened to be because there is such a closely related invariant measure, and the walk on the tree that is given by an invariant measure behaves like the walk on the original tree. But here, for these lambda biased walks, there is still an invariant measure, but the Radon-Nikodym derivative between this measure and the original measure is more complicated, so it creates a biasing, and this formula turns out to be wrong. We do know that this formula is wrong. We don't know what is the right formula. And so I should say this, and so on this problem, so we have 2 papers actually after this, one follow-up which considered the lambda biased walk, where we showed that the speed does exist. It's and it is positive in this range. And we raise the question, is the speed monotone in lambda? Okay? And in general, this question is still open. So you move this lambda parameter between 0 and m. You have a Galton Watson tree without leaves, so maybe let me state this as a question. So on a Galton Watson tree with no leaves, is the speed as a function of lambda monotone. And of course, we expect the speed to be decreasing because as you increase lambda, you're increasing the weight as going towards the root. The process is still going to infinity, but it should go slower and slower as lambda increases. But we don't know it, and until last year, there was really no progress on this question for 17 years or 16 years. So is the question clear? Okay, so I'm still very interested in the area we're most interested is near lambda equals 1. Lambda equals 1 is the only place where we have a simple formula for the speed. And there's still no progress near lambda equals 1. But last year there were 2 papers on this problem. So one by Benarus, Freeberg, and Sidorovicius showed the answer for this type of question is yes, not just on this Galton Watson tree, but on the general one without leaves for certain range of lambda. So lambda between 0 and 1 over 717. Okay, but as I said, nothing was known on this before, so this is certainly progress, and it's a very, very elegant and clever argument. Then a few months after, Eli Dacon found a kind of formula for the speed as a function of lambda. Now, this formula is not so explicit, so I should say that this, for speed of 1, there is a very simple formula coming from this logic. It's just the expectation of z minus 1 over z plus 1, which, note, that is by Jensen inequality, it's strictly less than expectation of z minus 1 over expectation z plus 1. So this would be the speed on a kind of regular tree with the same mean as our Galton Watson tree. And this is the actual speed on the Galton Watson tree. So there is a slowdown due to the randomness. And for other lambda, there is no formula like this. But Idecon does have a kind of more complicated formula that involves itself some properties of the random walk. And this formula still enabled him to show yes for lambda between 0 and 1/2. So now, things are getting hotter, closer to the most interesting value for us of 1. Yes?
What is Z?
Z is the offspring distribution. So the number of children of a node. Okay? So it's a random variable which represents the number of offspring of one vertex. Okay, so this was in this old 95 paper. For other lambdas, the formula that Idecon has is much more complicated, but it still enabled him to prove this. But the formula still hasn't been able to push beyond this value. Okay, so that's one challenge. So, all right, so now I want to switch to something else unless there are questions here. So I'm still going to talk about infinite graphs, but different type of problem now. Instead of speed, I want to go back to classical question of recurrence transients. And I want to give you several, again, we're going to try to get everyone involved in the questions. So my question is, which of these processes is recurrent, which is transient? Since my processes will not all be Markov chains, I should say what I mean. So by transient, I mean that the particle goes off to infinity, and recurrence just that it returns infinitely often to a compact set. So here is one And what we want to do is somehow to take the classical thing we all know, that simple random walk in ZD is recurrent for dimension at most 2 and transient for dimensions 3 and higher, and see what happens if we try to change the process in some ways. So here is the first example. So you to simplify life, I'm just going to consider processes that will be martingales. And here is the first one. So this will be a process in Z2 in the two-dimensional lattice, and we walk up or down for times t that are, say, between 4 to the k and twice 4 to the k. And we walk left or right, equally likely for times t, which are between twice 4 to the k and 4 to the k plus 1. Okay, so, and this is for all k. All right, so you start with k equals 0. So in step 1, you walk vertically, then you walk horizontally for a few steps, then you walk vertically for more steps, and so on. So this is a process in Z2. And, well, is it recurrent or transient? Is it go off to infinity or stay in place? We'll come back to this. So here is the second process. Any question about the definition of the process? I want to give you several examples, then we'll discuss them all together. So if we are at the vertex V, so if the vertex V is visited before, and horizontally if not. Okay, here is one more example. So I'm going to again look in Z2. So these walks are in Z2, but they're so-called not elliptic, so we have some favored direction at every time. So now I want to consider elliptic walks, meaning that at every step, the distribution, the particle can jump in all directions with probabilities that are bounded away from 0. And here is a specific example. So on this part of the plane, we're going to walk with probability 0.3 up or down, 0.3, and 0.2 left or right. And the same here. And the same actually on these diagonals. Okay, but on the other part of space, we're going to do the mirror image of this. So here we're going to walk with probability 0.3 to the right or the left, and only 0.2 up or down. Okay, but on both of these diagonals, on the diagonals we're going to do the big probability that. Okay, so on the right, on the left, we're more likely to move up or down, and similarly on these diagonals. But below and above the diagonal, we're more likely to move left or right. Okay, so again, this is a martingale at every point. And it seems very close to simple random walk in Z2, but is it close enough? Is it still recurrent? Or have we made some big change and it's transient? And maybe, so this is the third example. I'll give one more. So fix, so in Z3, fix two measures, mu1 and mu2, which will be three-dimensional measures. So they're not three-dimensional probability measures, so they're not supported on some hyperplane in Z3. They'll have mean 0, and they will have bounded support. And now the rule is as before: if the current location is visited before, then the next step, xt plus 1 minus xt, will have distribution mu2. If not, then xt plus 1 minus xt will have distribution mu1. So the question here is we have two measures, mu1 and mu2, and each one is a classical kind of three-dimensional distribution of mean 0, bounded range. And so we know that if we just say take a random walk with mu1 forever, it will be transient. It's just like simple random walk in Z3. The same if we take a random walk with mu2. But now we combine them in some way, which is adapted. It's based on the past. For instance, when in visited verses we do one thing, in other ones we do the other thing. Is this process transient or recurrent? Okay? And I could give 5 or 6 more examples, but maybe this is a good point to stop and again use democracy to decide what's going on here. So, example 1, recurrent or transient? Okay, who? Well, here there's no third option really, because
well, maybe undecidable.
okay, but it's even if it was undecidable, it would still be either recurrent or transient. We just couldn't know. But anyway.
Well, then either has to be correct.
All right. Anyway, it's not undecidable. It's easily decidable. So the first example is it's easy. So it's a process in Z2. Who thinks it's transient? Raise your hand. Oh, okay. All right. So everyone else thinks it's recurrent. So all right, who can tell us why? Yes?
Well, my guess is because of the increase in time ranges, the fluctuations increase, borders, relative each time as you start going back in bigger circles or something like that.
That's the right. That's the right image.
If it would be same time scales, I would think it would be recurrent.
The same time scales.
Well, not increasing time scales for going up, down, or left, right.
Yeah. Right. So it's one reason it's easy to see is suppose I want to ask, in these horizontal steps, is it going to reach the origin? Well, how is it going to reach the origin in the horizontal steps? Only if right before this round of horizontal steps, it somehow reached exactly the x-axis. But right before this, we did a lot of vertical steps, like 4 to the k vertical steps. So the chance that in this round of vertical steps, we reach exactly the x-axis is 1 over square root of 4 to the k, approximately, right? So about 1 over 2 to the k. So it's very small chance that at the end of this round, we reach this x-axis. And if we didn't, then all the horizontal moves we make won't bring us back to the origin. Okay? And similar logic applies, for when you switch the horizontal and vertical. So just from Borel-Cantelli, you get that the number of rounds that you could visit the origin is finite. So after finitely many rounds, you stop visiting the origin. The same thing applies to any specific site. So the path will have to go to infinity. Okay, that was an easy one. What about 2? So If a vertex is visited, you do vertical, otherwise horizontal. So I don't know. So this is weakly undecidable. we still don't know. So this is a question of Itai Benyamini, and it's specifically raised in a paper of Benyamini, Kozma, and Shapira. And this looks like a very simple process. My weak guess it's probably recurrent, but we don't know.
Let's vote.
What?
Let's vote.
Let's vote. Okay. This one. Okay. Who thinks? So is it clear how this process behaves? What? Did someone say it's not clear? Okay. All right. So we'll vote on this one. Who thinks it's transient? Raise your hand. Okay. So it looks like such a small perturbation of simple random walk, right? How could it be transient? But in fact, it's transient. So here's a quick. So here are some transience criteria that. So this is after all a countable state Markov chain, and so if you have for countable state Markov chain, so we have a chain P, right? And we're only going to look at irreducible chains. So the chain is recurrent if and only if, but I just need this direction, if any superharmonic function so superharmonic function just means that the function u is bigger than p times u, so you take the matrix P and just multiply by the vector u. Any superharmonic great non-negative function is constant. And this is in fact if and only if, okay, this is very, very easy to see, because if U is superharmonic, then it means that, so both directions are true, but I just want this direction, and the proof is that if you look at U of xn, this will be a non-negative supermartingale. Just what this inequality means is that the expectation of U at time n+1 given xn is decreasing, so it's a non-negative supermartingale, so it will converge. But if the chain is recurrent and irreducible, then it's going to visit infinitely often every state. And if U of xn is converging and we revisit every state, U has to be constant, right? Okay, so that's one easy criterion, but that one is not so easy to directly apply to this problem. So the other criterion we need is that, so P is recurrent, again if and only if, but I just need this direction, any excessive measure so excessive measure, I mean that nu is bigger than nu times p, is invariant. Okay, so we have a measure nu, which is a positive measure on the state space. We don't assume it's finite, but it's a positive measure. And it satisfies the inequality that if you take nu and you multiply by p on the right, then nu is greater than nu times p. In the recurrent case, this forces nu to be invariant, so nu actually equals nu p. And this is if and only if. Okay, and let me remind you why this is true. Okay, because so why is this true? So first of all, there is a natural definition of a measure. So for p which is recurrent, you fix some starting node A, and you define pi of x is the expected number of visits starting from A until the first return to A of x. Okay, and then it's a classical exercise that I will leave you to check that this pi in the recurrent case, so you know that tau A, the return time, actually I should write tau A plus. So this is the first positive return time to A, and this is invariant. This is an easy classical check that you can do yourself or find in a million places. So this measure is invariant, and now you just define the time reversal with respect to pi. So p hat of xy is defined by pi of x times p hat xy equals pi of y pyx. Okay, and this, because pi is invariant, this defines good transition probabilities. So p hat is just the time reversal of p, and the chain defined by p hat is still recurrent, because if you look at p hat to the n of AA, this is just the same as p to the n of AA. So when you sum this for n goes from 0 to infinity, you must get infinity. So p hat is still recurrent. But now if you compute, look at the function nu over pi, and compute p hat times nu over pi, so at a point x, so this is sum p hat xy nu of y over pi of y, which, because of the definition of p hat, this is the sum over y of pxy over pi of x nu of y, which, because of our assumption that nu is bigger than, and let me actually write the nu of y on this side. Okay, now this is exactly 1 over pi of x times nu p of x, which, because of our assumption, is greater or equal than nu of x over pi of x. So you see that the function nu over pi is superharmonic for p hat. I got the directions wrong though. This is right. So our assumption was that nu is greater than nu p. So we have this inequality. So the function nu over pi is superharmonic for p hat. So we get so we get from the first criterion that nu over pi is constant, which means that indeed nu is invariant. Now, how do we apply it to this exercise? Well, look at the function nu, which is identically 1. Okay? So at any x, so you can check that nu x equals nu p of x at any x except the origin, but at the origin, nu of x is 1, but the total contribution from all the neighbors is just 0.8. So nu p of the origin is 0.8, nu of the origin is 1. So the function 1 is an excessive measure. So this process is transient. Okay, so this kind of computational proof doesn't really explain probabilistically what is going on here. Why is this process transient? It tends to move more in the less in the radial direction and more in the transverse direction. And so finally, I want to move to the ones that are new. So this kind of process, number 4, it turns out this kind of process is always transient with 2 measures. And okay, any questions about this? So here is a general theorem, which is joint work with Sergei Popov and Perla Susi, and it says that if so an adapted walk in ZD given by 2 d-dimensional measures of mean 0 is always transient, but it's false for 3. So what I mean, in this process, we have 2 measures, mu1 and mu2, and we decided in an adapted way, based on the past, which one to use in every step. Okay? Now, any process like that in Z3 or any dimension which is 3 or higher will be transient with 2 measures, but with 3 measures, you can already construct a counterexample. In 3. Okay? So in fact, in D dimensions, you can construct an example with D measures. Okay, so I want to end today by proving this to you, and so to prove this, we want to start by saying what proofs do we know that, say, simple random walk in Z3 is transient, and then see of these proofs which one might generalize. Okay, so one proof is by explicit calculation, combinatorial calculation of return probabilities. Another, which is closely related, is by local central limit theorem that will compute the return probabilities and then you sum them up. Another, which is again related, is Fourier transform criterion for transients, which is goes back to Fuchs and Chang. Another proofs which work in the reversible case are based on electrical networks and flows. What other methods do you know to show that Z3, random walk in Z3 is transient? So it turns out this method of superharmonic functions, which is more known under the name of Lyapunov functions, is very effective, and it can be adapted to this setting. So let's go through this method. So first, so the method of Lyapunov functions we're going to find a function phi that tends to, so phi will be a positive function. It tends to 0 as x tends to infinity. And expectation phi of xn plus 1 given, given everything we know at time n, will be less than phi of xn, if, well, let's just put it this way, okay? This will be true, and this will force so now, so then if you know that lim sup of xn is infinity, then xn is transient. And this is not just for Markov chain, but for any process. Because our process here is not a Markov chain. It decides based on, so it's an adapted process, but to some sigma fields Fn, but it decides based on the whole history, not just on the last location, where to go, right? Because which measure we use depends on the whole history, right? So we want to apply this lemma, and the proof. So for all our processes, the fact that the lim sup is infinity is almost trivial just by calculating the variance, because the variance grows to infinity, so it's impossible that the process will stay bounded. And then, but the reason this lemma is true is just again by super-martingale convergence, because this assumption here means that the lim inf of phi of xn will be 0, but phi of xn will be a positive super-martingale. It converges, so phi of xn will go to 0, which will force xn to go to infinity. So, because phi will be positive everywhere, only going to 0 at infinity. So the whole game is to find this Lyapunov function. What?
Do you want your phi to be convex?
No. We just want, so this superharmonic condition is close to convexity, but we don't need any convexity assumption. You see, I mean, the proof of this didn't use any convexity. We just used the superharmonic property. This inequality here just means that phi of xn is a super-martingale. So you can just, and it's a non-negative super-martingale, so you just apply super-martingale. Phi of xn goes to 0, and that implies that the norm of xn goes to infinity. So let's first apply this in the standard case of one random walk. So to first consider one standard random walk in ZD where the increment, so xn plus 1 minus xn, has some law mu. Now, the covariance matrix of mu is going to be a positive definite matrix. So this is, right, if Z has the law mu, then if I look at the expectation of Z transpose, which is just expectation of Zi Zj, this is the covariance matrix of mu. This is a positive definite matrix. So I can always choose a basis in which this covariance matrix is diagonal. So in other words, by shifting replacing the increment Z by some U times Z, where U is a unitary matrix, we gives that so we can diagonalize this matrix to get a, just a diagonal matrix. So we assume we just really replace, we assume that UZ is the original Z, so we're just going to assume that this covariant matrix M, expectation of Z Z transpose is itself already diagonal. Because, right? Because if it's not, then I just multiply by this unitary matrix and I make it diagonal, and of course this won't affect recurrence or transience. Okay? Now this will be tricky when we have several measures, but with one measure we can certainly do that. And okay, so okay, and now let's take the function x minus 2 alpha, and we're going to truncate it at some value. Okay, so we're just going to take functions which are power laws. Alpha will be a small positive number, and now we want to check that this is a Lyapunov function. So, you know, this is just a calculation, but let's do it anyway. So, and we want to check that this is a Lyapunov function. So to do that, we need to remember, you know, some Taylor expansions. So let's write this down: 1 minus alpha y plus alpha alpha plus 1. Just the Taylor expansion of the binomial for small y. And we want to apply this to this ratio of norms. So let's write this norm. So when we expand the top, we get 1 plus x transpose. Right, so we take plus twice x transpose z over norm x squared plus z transpose over norm x squared. Okay, so now if we take this to the power minus alpha, what are we going to get? We'll get 1 minus 2 alpha x transpose z over norm x squared plus minus alpha z transpose over norm x squared. I mean, there's a reason I'm doing this calculation, because we want to see something popping out here, and then, okay, then we need the second order term, and we'll throw away all the third order terms. So in the second order term, we get alpha, right? So we have to look at the squares. So we get alpha alpha plus 1 over 2 times the square here. We'll get 4 x transpose z. Well, x transpose z is the same as z transpose x, because this is a number. So I write the square of that like that. And we divide by norm x to the 4th. And then everything else can be bounded by norm x to the minus 3. So in this calculation, x represents our current location, z represents our increment. Z is bounded because we have bounded increments, and think of x as large. Okay? So when you square this, when you square this thing, you get the square of the first term. That's what I wrote here. But if you look, say, at the cross term here, it will already be of lower order. It will be thrown into this x to the minus 3 term. And similarly, if you square this will be even smaller. This will be x to the minus 4. So neglecting these errors, we get this expansion. Okay? And all right, so what does that tell us? Now we want to look at phi of x plus z and compare it to phi of x, right? We want to see that this is less than 1. So this is just the quantity we have here, this to the minus alpha. So we get that this is, well, I'm going to write less than. And here I'm assuming that x is large, so x is larger than our 0. And then what do we have here? So I want to take already the expectation, because what I have here is exactly phi x plus z over phi x. So what happens when we take the expectation of this? So because the increments z have mean 0, this is just going to vanish. And when we take the expectation, we'll only get the other terms. So we'll get 1. From everything else, we can take out alpha. And I want to also take out the x to the 4th. And then what is left is expectation of minus the expectation of norm z squared, norm x squared, so the norm x squared is because I took x to the 4th, and then I also have a plus twice alpha plus 1, and x transpose, I'm sorry, x expectation, let's see, okay, x transpose, expectation of z transpose, which is just m times x. Okay, plus norm x to the minus 3. Okay, and this, and we're almost done here. Let's write it in terms of, let's see what's the coefficient of xi squared in this. So we get 1 plus alpha over norm x to the 4th, sum I from 1 to d, and then what multiplies xi squared? So from here we get, so the expectation of the norm z squared, this expectation is just the trace of the covariance matrix M. So xi squared multiplies minus trace of M, right? Because look at the definition of the covariance matrix, it traces just the sum of the means of the I squared, and plus twice alpha plus 1 lambda I, because remember we took M to be a diagonal matrix. On the diagonal we have xi, so this is the final answer here. Okay, and now you see what is the condition we need. Right, so if trace of M is strictly bigger than twice the maximal eigenvalue, then there is some alpha where expectation phi x plus z over phi x will be less than 1. Remember where z has the distribution mu, right? Because if the trace of M is strictly bigger than twice any eigenvalue, then you can stick in some small positive alpha and still get the inequality that it's right. So we want, if this is true, then it's also true here, multiplying by some small 1 plus alpha, right? And okay, and then what you get is that this contribution is negative, and of course you still have an error of order norm x to the minus 3, but what we have here is of order norm x to the minus 2, because we have x to the 4th here and x squared here. So the error is really negligible, and we get the super martingale property for large x, which is all we care about, because for small x we don't have to worry here, because we take a minimum with a constant. So this verifies the super martingale property under this assumption. So if you have simple random walk, simple random walk, the covariance matrix is 1, 1, 1, and you are fine. The trace is 3, and you see how two-dimensional, simple random walk in 2 dimensions, of course this doesn't work. The trace is exactly twice the largest eigenvalue. Now what do you do if you have one measure and the covariance matrix doesn't look like that? What if the covariance matrix is, say, 5, 1, 1? A random walk like that, right? It walks, say, 5 in the x direction, 1, 1 in the y and z direction. This is still transient, But this argument, as I told you, it doesn't prove it yet. So how do you modify to make it work? You just contract the first coordinate. So the point is, if I want to understand if a walk is transient, if I multiply the walk by a matrix, that doesn't change whether it's transient or not. So I can just multiply by a suitable matrix A. It's not going to be unitary. It will just be, in this case, it will just be the matrix, which is 1 over square root of 5, 1, 1. And if I just multiply my walk by this matrix, it will transform this covariance matrix to just 1, 1, 1. And I'll be back in good shape. So for any covariance matrix, if I just, before starting the walk, I just multiply the steps by the inverse of the square root of the covariance matrix, then I make the covariance matrix the identity, and this argument works fine. Now this was all reproducing the stuff we all know, that one measure gives us a transient walk. But now the key is that this method does work for several measures. So what if I have just two measures? So any questions about this? So if I have two measures, I have two covariance matrices, and the key, what this argument gives us is the following general lemma. Given adapted walk determined by the measures mu1 up to mu k, and I'm not going to repeat, all these measures are well, I will repeat, they are d-dimensional in ZD, mean zero and bounded support. Let's write mi for the covariance matrix of mu I. If we can find one matrix A, and it's crucial that it's one matrix A, so that the trace of A times mi times, so I want, say, A transpose MIA, that this trace, okay, let's put the transpose here, is strictly bigger than twice the lambda max of A MI A transpose. Then walk is transient. So this is the nice feature of the Lyapunov function method. It didn't depend on the fact that we have the same distribution at every step. As long as at every step we satisfy the supermartingale property, we're fine. And this is the condition we need in order to satisfy that property. And we don't need it for the original walk. It's fine if it holds after multiplying by a matrix. So this just boils down to a linear algebra question. When can we take our covariance matrices and rotate them, or it's not rotation, it's conjugate them by some general matrix A to get this property? And so let me show you that you can always do this for two matrices. So for two matrices, it's enough to do it in dimension 3, because you can always look at the 3 coordinates of the walk. So let's take d equals 3, k equals 2. So we start with two covariance matrices, M1 and M2. Now you can always rotate to make one matrix the identity, just using a unitary transformation. So we can already assume that M1 is the identity, M2 has been transformed somehow. Okay, M1, we first rotate M1 to make it like that. Then we can make M1 the identity just by multiplying by the inverse of the square roots of the eigenvalues using that matrix, and M2 changes. Okay, then we rotate again. This time now we rotate so that this matrix M2 becomes diagonal. So when we rotate, the identity doesn't change, because if you conjugate the identity by a unitary matrix, that doesn't change anything. And we'll get that M2 prime will become some diagonal matrix, which I'll write as ABC, where I can assume that A is bigger than B is bigger than C. But now we can multiply by one more matrix, which will give us here B over A, 1, 1, and here B, B, C. So the matrix we're multiplying by, in this stage, will just be the matrix root B over A, 1, 1. Just this diagonal matrix, if we conjugate with that, these matrices will transform to this, and now we're in a good situation. This pair of matrices both have trace which is strictly bigger than twice the largest eigenvalue. Right here, B over A is less than 1, and here B is bigger than C. So each of these matrices is good, and so now we're set, and we know that the walk is transient. So the challenge is to do this in higher dimensions, and in higher dimensions, the critical k is d. So for k less than d, you can do it. This is actually something that's not written up, but so this is a linear algebra fact, which is currently, I would say, work in progress with Fedya Nazarov, just to verify this linear algebra claim that for k, which is less than d, you can always find these matrices. So we have a way to do it. It's quite painful. So if I'd still be interested if someone sees a simple reason why. So here's the general statement. You have d minus 1 matrices which are strictly positive definite in d dimensions. Then you can always find the matrix A that will move them to have trace strictly bigger than twice the second eigenvalue.
What is strictly bigger than?
So what we want is just to satisfy this lemma, the trace strictly bigger than 2 lambda max. So we want to show that, I mean, this lemma, if k equals d minus 1, then you can always find this matrix A.
D minus 1 matrices, then you can do it in dimension z.
Yes.
It's A, which simultaneously moves that.
Yes, yes. So this is something, okay, it's, well, I think it's true. I mean, we have some handwritten sketch covering many pages, but, it would be nice to, so we will write it up if no one comes up with a simple explanation. Now for k equals d, this is impossible. And indeed, so I'm finishing now in 1 minute. I just want to finish with the example that shows that for d measures, this doesn't work. So, and let me give you the example in 3 dimensions because it generalizes readily. So here is a walk in 3 dimensions, which just has 3 measures. So we move from so we are at a point x, y, z. And how is this point going to change? Well, let's look which is the biggest coordinate. So suppose that x is bigger than y and bigger than z. Then what we're going to do is x will go to x plus or minus 1. Each of them with a probability 1 minus 2 epsilon over 2. And then y will go to y plus minus 1 with probability epsilon over 2 each, and z will go to y plus minus 1. I'm sorry, to z plus minus 1 with probability epsilon over 2 each. Okay, so we take the largest coordinate, and with probability 1 minus 2 epsilon, we move it equally likely up or down. With probability epsilon, we move each of the other coordinates. Okay, so this you do in 3, and of course you can generalize it in any dimension. You move the highest coordinate. So this is kind of the opposite of what the example I drew before in 2 dimensions, where we would always move the lowest coordinate. Here we always move the highest coordinate, and this tends to make the process more recurrent. So this is a process with just 3 measures in 3 dimensions. Okay, you have to say how you break ties, but say you break ties lexicographically. Then this process is recurrent in 3 dimensions, provided epsilon is small enough. The proof is based, again, using Lyapunov functions, but it's much harder than the proof I showed you. It takes several pages of calculation, so you can find this on the archive. Again, a challenge is find a simple proof and one which will be good enough to determine the critical epsilon. So I don't know for this kind of model what is the, I know that for epsilon large this is transient, for epsilon small this is recurrent. I can get some bounds, but they don't match. Okay, and with the current method it's so painful that I'm not even contemplating doing it. Right? We were very happy that we could show that for small epsilon. And it works in any dimension. The critical epsilon we find depends on dimension. So this kind of walk is recurrent. It's a very simple rule, right? So why not a simple proof? Okay, let me finish here. And thank you for your attention.